So are you ready?
Yes. Okay.
Okay. So let's start the afternoon session, which is the last session of the workshop. The first speaker is Professor Masahito Hayashi from SUSTEC at Nagoya University. He tells us Bregman divergence-based EM algorithm and its application to classical and quantum rate distortion theory. So please start.
Thank you for introducing me. So today I want to talk about Bregman divergence-based EM algorithm and its application to classical and quantum rate distortion. So firstly, I want to explain what is EM algorithm. So, sorry, this is a mistake. This must be small, so lowercase. So this is mistake. So EM algorithm is similar to EM algorithm, but this is different. So this is very confusing. So lowercase EM and uppercase capital case EM is different. Lowercase EM algorithm is very similar to capital EM algorithm, expectation and maximization, but it is different from capital EM algorithm. So indeed, so small lowercase EM has a E step and M step, but E step corresponds to maximization and M step corresponds to expectation. So this is quite confusing, and these are different objects. So EM algorithm is a generalization of Boltzmann machine. Boltzmann machine is a very famous structure related to the learning theory. Generally, lowercase EM algorithm is an algorithm to minimize KL divergence, Kullback-Leibler divergence between exponential family and mixture family, which is a key concept of information geometry. This is the EM algorithm for summary of this. This is, and I also introduce another concept, rate distortion theory. This is a different object. This one is somehow recently. No. This one has very long history. You are considering data compression. Data compression is a very famous method, and usually you use JPEG and some image picture. So in that case, when we want to handle analog data, so in that case, you cannot use conventional data compression. Conventional data compression means that the zip code or LZH code. This is a data compression for discrete data, but sometimes you have an image, so in that or somehow voice. So in that case, you need to different method for data compression for analog data. So rate distortion theory is one of the typical methods for data compression for analog data. So of course, in that problem, we can consider it's quantum analog. To make this, we need to solve a kind of minimization of mutual information under a certain constraint. Indeed, Arimoud-Brecht algorithm is known for this aim, but it minimizes a different quantity, which is a modification of original target function. So in this case, there is no efficient algorithm to solve the minimization related to the rate distortion theory. But many people are satisfied with that modification now. So this is somehow a problem. So maybe now you come many people. So maybe I will give you the file of the my talk. So maybe if you could not follow or if you want to check the definition of something, so you can check this one. So please use this if you need. Please use this file. So, sorry. So now we explain the task of the rate distortion. Rate distortion theory assumes that the data xn is generated subject to the IID distribution pxn. Px is one probability distribution, and we consider n times of IID extension of px. So in that case, receiver does not need to recover full information of xn. So this is general setting. So in that case, it is sufficient to recover some alternative random information yn such that the distance between the x and y is smaller than a certain constraint. This is something that rate distortion constraint for the rate distortion. So our data is external, but it is enough to recover this yn to satisfy this condition. That theory is called the rate distortion theory. So in the rate distortion theory, what we consider, so we consider this external. This is the distribution for our data, and we consider cost function dxn, and we consider conditional distribution y and w. So this one is, but we consider this constraint. So there is Pn as the source distribution, and we consider its conditional distribution, and we consider average of this one under the joint distribution. This Px and W gives the joint distribution. Under this joint distribution, we take its average about the error function. D express the error function. We consider that this error average error is smaller than C, 1 equal to C. This is a kind constraint. So we consider the set of condition distribution in that way, Py-Ax-C. So C is the constraint. So in that case, the minimum compression rate can be described by this minimum quantity. So we consider mutual information, and we consider this joint distribution. This joint distribution written as this one. This is our notation. Under this joint distribution, you can define mutual information. So we minimize mutual information under this cost constraint. So I will explain the definition of definition of mutual information in this way. So what is the mutual information? Mutual information is this guy. So firstly, we need to consider entropy. Entropy is this guy. So we consider random distribution Px, and we consider this quantity, average of log Pn. So this one is called distribution. So we consider entropy of x and entropy of y in the same way, and also we consider entropy joint distribution x and y. Of course, if x and y is independent, this entropy equal to the sum of each distribution, entropy of each distribution. But now we have this one has some correlation. So in that case, this sum of the entropy is greater than joint distribution. That difference is characterized by the mutual information. Sorry, this was a mistake. This one must be D. This one must be D. Sorry. So we consider K divergence. This one must be D. So K divergence means defined as this one. So this is one distribution P and another distribution Q. We need to consider the difference of logarithmic function. So and we take its average based on the distribution P. So this one is written by this one must be D. This is this one. So that mutual information has another expression in this one. So in that way. So of course, so please be careful. This one is somehow output distribution of y. So I define output distribution in this way. So input is px, and we have this conditional distribution. Then we have output distribution for y. So that output distribution is defined in this way. And in this way, this one is product independent distribution. But this one is joint distribution. So in that case, these two distributions different. We consider KL divergence for these two distributions. That KL divergence is equal to this mutual information. We need this very important formula. So, 10 minutes. So now I want to explain protocol for rate distribution. So in that case, we need some assumption. The data is subject to the IID distribution, independent and identical distribution PX. So we need this assumption. But in that case, initially we need to assume this process. This is the code construction. So before starting the real communication, we need to make this pre-processing. So because in order to make some communication, encoder and receiver, so sender and receiver need to make some agreement for their coding. In that case, they randomly choose M element. M element means that this is mutual information. Of course, in that situation, firstly, we need to choose some W. This is conditional distribution. Based on this conditional distribution, we can calculate this mutual information and its exponential quantity. So we randomly choose Y1 to YMN. So from the this N product set. So we primarily choose this element. That choice is somewhat slightly strange. So in the case of information theory, sometimes we need to make good code by using random. So random is somehow very carelessly, but very surprisingly, in the case of information theory, that kind of careless coding generation is more efficient than more systematic method. This is quite strange. So somehow that kind of construction is useless, but mathematically that kind of randomized construction is very powerful. So at least theoretically, this kind of random construction is very useful. Then we often use this method, and we then later when we start the real communication, sender make this encoding. So firstly, sender generate data external subject to the this IID distribution. Given that this data, encoder need to choose K as in this way. So we have a M candidate of some element. So in this situation, encoder need to find the most closest one in the sense of this cost function. So they need to choose closest one in the sense of D. Then this guy need to sender need to send information K to identify the closest one. So then encoder send this K. Later, receiver convert K to YK in this way. So in this sense, by using in this way, so with very high probability, this YK between the distance between this cost function between the xn and yk is smaller than n times c. We have this condition with very high probability. So in this sense, this method works very well. So also the optimality of this method is already known. So, but in that case, what is the remaining task? We need to find optimum conditional distribution in the sense of mutual information. So we need to minimize this mutual information under the this condition, under this condition. So this is our task, but there is no good method. Of course, this kind of problem can be extended to quantum setting. So now I want to explain the existing method. Existing method is called Brecht and Brecht algorithm. However, mainly this idea was done by Brecht. So in that situation, it is quite difficult that linear constraint. So they consider that this Lagrange multiplier by using S. S is Lagrange multiplier. So using S, so we have some weight function. Then they minimize all of the conditional distribution. So in that case, if we choose 3W-S, the minimizer satisfies this condition. Many people emphasize this, then many people consider that this problem setting is just it. But nobody plays that. How to find that kind of good S? This is the problem. So without explaining that point, many people satisfied this method. So this is quite a strange situation. Anyway, many people satisfied this method, but in real, this is not so good. Indeed, we have a slightly different problem, charge capacity problem. In that situation, Arimoto make a similar problem, and Breft also consider that similar problem. So Arimoto and Breft consider the maximization of the charge capacity, mutual information for the information transmission. In that situation, we don't need to consider that linear constraint. So due to that problem, their method works well. However, in the case of data distribution, we have this constraint, but their method cannot work with this linear constraint. Then they consider this alternative method. That idea is proposed by Breft. So Arimoto did nothing for that problem, but people consider that this method is called the Arimoto-Breft method. So now, in order to resolve that problem, we want to introduce another method, alternative method, information geometry. Information geometry has so many several kinds of problem setting. Most famous problem setting is somehow information geometry for the probability distribution. So in that situation, we consider exponential family. Exponential family is defined as this one. So firstly, we need to fix one distribution P0. This one corresponds to the origin. So, but in that situation, we want to consider parameterized family of distribution. In that situation, we consider some function Fyx. So using this Fyx, we need to consider this distribution. Of course, if simply you consider this one cannot satisfy normalization condition. Normalization means that the measure should be 1. To satisfy normalization condition, we need to calculate that function mu theta. So, considering this factor, so we have a normalization. So then we have a family of distribution. That kind of distribution family is called exponential family. Another famous distribution family is mixture family, or sometimes expectation family. Expectation family is this one. So we consider its expectation based on this random variable. So we have this distribution, and we take its average. Average should be equal to some constant. So we have several constraints. Maybe the number of constraints is D. So then we can define this mixture family. So this mixture family and exponential family is different objects. But in information geometry, these two kinds of objects are very important. Now you need to focus on that. This function, mu theta, is convex function. This is a very important point, because information geometry can be extended or generalized to the Bregman divergence. So this one is a very, very general setting. We can reconstruct that kind of geometric structure only with one smooth convex function. So once we have one convex function, mu g, then we can recover same discussion very easily. So in that situation, exponential family can be given us in that way. So E is some vector. So now we consider m-dimensional vector space, real vector space, And we have several D independent, linearly independent vector, and we have another vector E0. So then we have some summation. So this kind of space, this is almost linear, but we have this shift of situation. Then this one can be considered affine space. So that kind of affine space is called exponential family. And we consider its partial derivative. So we consider its partial derivative, and we consider that this one. This means that we take partial derivative in the direction with vector EI. In that situation, we need to calculate this quantity. That kind of derivative has some constraint in this way. Oh, sorry, this. So this is again mistake. This one must be I, not J. This one I. This one must be I. Sorry, this is I. So we take summation about J, then we have I. So this is mistake. I run to the 1 to D. And this one, sorry, this is mistake again. This one J run 1 to from 1 to M. Because now we have an M-dimensional system. So the number of input real numbers is M. So, but now we have D vectors. So in this case, this one must be I, and this one 1 to D. So this is a mistake. So anyway, so we need to consider that element of G to satisfy this condition. This one is called the mixture family. So in that situation, you can define Bregman divergence in this way. So you need to consider this partial derivative, and you take this difference and this one. So this one can be okay. This one can be characterized in that way. So very simple way. So this one is a function. This is convex function mu G. And we have a tangent line in that way. So the G1 is at some point. We want to consider its tangent line. So then we focus on the another point of G2. So in that case, we need to focus on this difference. This quantity is always positive because this one is a convex function. Then we have this positive quantity. That difference is characterized by that divergence, because divergence is this one. But of course, somehow this looks complicated. But if you write down that this picture, this quantity must be always positive due to the convexity. So you can easily imagine this quantity. Indeed, that kind of information geometry for the probability distribution can be recovered by Bregman divergence. So previously, I explained that defined that this cave divergence in this slide, but this one has some type. This one must be D. This one must be D. So you replace D, and we consider this one. So in that case, this one equal to this Bregman divergence. So in this way, it is enough to consider one convex function defined by this way. So everything can be restarted from this convex function. That kind of situation can be extended to quantum states. The case with quantum states. So in that case, exponential family in the quantum states can be defined by in that way. So this is Hermitian matrix Xi, and we have some one Hermitian matrix, and we have this one. So almost the same. Fx can be changed to the one Hermitian matrix. So then everything same. So also mu theta is defined by the same way and this way. And that kind of expectation, previously we consider expectation of this one, but now we have this one. Also, this is the expectation. So then we have a mixture family. So in this sense, also we have this equation. So this is quantum relative entropy. Sometimes this is called omega entropy. So that kind of quantity is equal to the this Bregman divergence. So then, even in the quantum setting, it is enough to consider Bregman divergence with this convex function. This one is also convex function. So now I want to explain very important theorem. So once you have one convex function, you can recover this Pythagorean theorem. So divergence satisfies Pythagorean theorem in that way. So here is the mixture family, and this is exponential family. So in that situation, the divergence between the theta 1 and theta 2. Of course, this is not symmetry. So in this situation, theta 1 needs to be element of mixture family, and theta 2 is the element of exponential family. So in that case, the divergence of theta 1 and theta 2 equal to the sum of these two mixed divergence. Here is a mixture family, and this is the exponential family. So we have this equation. So in that situation, this is very important. So in this situation, this one is the most closest point. For example, this is theta 2, and we want to find the most closest element among the mixture family. That element is equal to this one. So that point, theta 3 can be considered as the M projection. From this one to this one is called M projection, and from this one to this one. Well, this point is the most closest exponential family element from theta to theta 1.
Can I ask you a question, Masahito?
Yes.
So uniqueness of this point, the uniqueness
Yes.
of the point minimizing
Yes.
the distance, is it proved?
Yes, of course.
For these two families?
Hmm.
And for more general convex set, what do we know? Or is it very difficult to prove in general?
General, but general convex in the case of this one is always written as any somehow convex linear convex family can be written as this one. So then, in the case of all of linear family can be described as mixture family, then it is okay.
Okay, thank you.
So in this sense, Pythagorean theorem always holds. So, but we can discuss this kind of problem for general convex function. So this one includes a set of probabilities and a set of quantum states. So this is very generic situation. So now I want to explain the EM algorithm for the with Bregman divergence. This one is already studied second person. But in that situation, we want to consider minimization problem. So what is this? This one is this one. So we have one mixture family and exponential mixture family. We want to minimize the this element. This one must somehow here is an element of mixture family, and here is an element of exponential family. We want to minimize this. So, but how to make this one? We start from this one, and it is enough to consider E projection this way, and this next one is M projection, and E projection, then continue this way. So then maybe we have some convergence. So of course, this one is monotonically degrading, because please focus on this guy. This guy is smaller than this red one, because this one is maybe slightly difficult, but this one is somehow should be orthogonal. This projection, then orthogonal. So then sum of this divergence equal to this guy. So this means that the difference of divergence this green and red is this one. So in this sense, divergence is decreased. And similarly, this divergence can be written as sum of this one and this one. So in this sense, this one is smaller than this one. So then you can monotonically degrade it. However, there is of course you can we can always have some convergence and this monotonically degrading, but sometimes there is risk that the convergence point is local minimum. So this one has some open problem. So one of my contribution is global convergence under this condition. Or if this condition is held in the generic way, so for two mixture element, mixture family element, and this is projection. This projection is always smaller than original divergence. If we assume this assumption, we can always show that this algorithm converges global minimum, and the convergence speed is smaller than this one. I could prove this one. Of course, this convergence speed is very slow, but really this convergence speed much quicker. But in order to prove the much better evaluation, we need more assumption or something. So, but we have a more result in my paper. So I want to show only the preliminary and easy result. So now we want to back to the original problem, rate distortion theory. So in that situation, we need to minimize this one under this condition, and our distribution is this family, this one. So this one. So this one means that joint distribution satisfies some linear condition. This one means that this family is this joint distribution has a one mixture family. This is mixture family. So then we can apply EM algorithm to this problem. So this problem can be written as this minimization, and this minimization can be written as of course this one is in this situation we have this one, but if we react this distribution family in that way, optimum this minimizing this one is equal to this marginal distribution. So in this sense, we have a form of the EM algorithm in this way. So this one has some mixture family structure, and this one satisfies exponential family structure. Also, this one satisfies the convergence condition in this way. So because this is only the take the marginal distribution. So marginal distribution equal to the this divergence between the marginal distribution. This one equal to this one because here is the same distribution, independent distribution. So then convergence condition falls. So then you can apply generic EM algorithm to this rate distribution problem. So, but in this generic state, in this specific state, situation, we have an E step and M step. Please, I want back to E step is E projection, and M step is M projection. So in this picture, so this is E step, and this one is M step. So how can I describe that E step and M step in this problem? In that step, in this situation, E step is very easy. It is enough to consider margin distribution. So we have a one distribution X, and we have this conditional distribution. Then you need to take, I forget Y, sorry. You need to take marginal distribution for Y. So then each step can be done very easy. And M step is slightly difficult because we need to satisfy some linear condition. So linear constraint condition. But that kind of linear constraint condition is converted to the this condition. This is somehow so trivial, but this one is very easy because this is one convex function for tau. So then it is enough to consider some minimization and minimize this convex function minus c tau, Considering that minimization with minus t tau, you can find the solution of this one. So one parametric minimization, very easy. You can apply the bijection method. So maybe you can use mathematical by solving this kind of one parametric minimization. So then you can repeat this one. So this is very easy. So I made some numerical calculation. So I consider that situation Px distribution is this one, and we have a cost function in that way. And then and also we consider constraint C equal 1.5. So then we have an optimal conditional distribution in this way. And this is my solution. And this minimum mutual information is 0.1 something. This one. So this is my numerical result. So we have this one. So the error, and this one is minimum one. In order to get minimum one, I made t equal to 100 or 200 or something. So, but already saturated. So this is almost close to 0. So I consider that difference, but this is very quickly go to 0. Difference very quickly go to 0. But my upper bound is very slow. In this sense, that kind of upper bound is not so tight because I only consider very generic, very weak assumption. If we assume much more stronger assumption, we have a much better evaluation. expression, we can show that the expression conversion. But to prove the expression conversion, we need more difficult discussion. So I want to skip that part. And also, I check the behavior of the optimal tau. Optimal tau is somehow this. This tau is related to the Lagrangian multiplier. This one. So this one. So in order to get a good tau or this parameter, we need to consider this way. So in each step, optimal tau is not constant, but after around 40 rounds, so this is almost constant. So this is maybe this is optimal.
Hayashi-san,
Yes.
we have some problem in audio.
What?
Someone cannot hear your voice.
Why?
I'm sure, but please check chat. Francesco complained about it.
Maybe when you, I don't know, when you went a bit far from the screen, I couldn't catch very well. I don't know if it is only me or.
So which part I need to repeat?
This one was okay. It was only me. If it is only me, it's okay.
Okay, I understand. So then I made this numerical calculation, and we have further result in this way. So we made various type of evaluation for EMRs. So I explain only one inverse linear evaluation, but if we assume more conditions, we can show that exponential convergence. So we have several, and also I discussed a much more complicated situation. And also we can apply our result to the quantum setting. So, but I want to skip this one because we don't have enough time. So we want to skip quantum setting. And this is the conclusion. We have studied the convergence of EMRs under the framework of Bregman divergence. So then, due to that generality, this result can cover the classical and quantum setting. And we have applied our result to the rate distortion theory. And our algorithm rapidly converges the true value. So thank you very much. This is reference.
Okay, thank you very much for an interesting talk. So are there any questions, comments?
Can I ask something?
Yeah, please.
So the talk was very dense, so I didn't catch everything, but I wanted to ask you, so what I know is that you can minimize on the right-hand side of the relative entropy, or you can minimize on the left-hand side of the relative entropy. And usually it is better to minimize on the right-hand side. In many problems, is more natural. So here, where are you minimizing for the relative entropy?
Relative entropy is omega T is omega K entropy. So this one is omega K entropy in the quantum setting. So we consider minimize of this one. So theta 1 belongs to a mixture family, and theta 2 belongs to the exponent family. Of course, you can switch this order. We minimize this quantity.
I see.
So we need to move both.
I see. Thank you.
So in this sense, we consider that minimization. But that kind of model is already discussed so many people. So in the context of how to say machine learning. So this kind of iterative algorithm is very common in the machine learning. So, but usually people, for example, hidden Markov case, they consider capital EM algorithm. That kind of expectation step is correspond to the expectation step corresponds to this M projection. Expectation corresponds to M projection, and maximization means that maximal language. Maximal e-protection. So somehow usually EMR is different from this EMR opposite. So, but capital EMR is much familiar. Lowercase EMR is very minor. Only few person understand. Because you need to understand the lower EMR, you need to understand the information geometry. But only few person understand the information geometry. Because this one requires somehow slightly difficult mathematics compared with other theory in machine learning.
Thank you.
Okay. Are there any questions, comments? If not, may I ask some simple question?
Yes, please.
Yeah, it seems Bregman divergence has very general
Yes,
concept.
very general.
So
Yes.
I mean, we have to choose some convex function.
Yes.
And so you explained on some specific choice of convex function, we recover KL divergence. Is it
Yes.
correct?
Yes,
And
of course.
so did you take a different kind of convex function?
This is a typical type of convex function for the
No.
also in the case of quantum case, this one. Of course, we can consider general one. Of course, in the case, if you want to consider Markovian process, you need to consider Perron-Frobenius eigenvalue of the transition matrix. If we consider a transition matrix, so if you want to consider geometry of transition matrix, Markovian process, in that case, this convex function is given as a Perron-Frobenius eigenvalue, logarithmic of Perron-Frobenius eigenvalue. So in that case, you can generate information geometry of hidden Markovian process.
No. My question is, do you use the same convex function or you choose different one? Different one. So this is a
yes.
So this is an advantage of your theory.
Yes, of course, we can apply more general setting by several setting related. Maybe this one extend to the Markovian situation. Markovian geometry of Markovian process somehow related to one convex function. That convex function can be defined by using the Perron-Frobenius eigenvalue. By using the Perron-Frobenius eigenvalue, you can define one convex function.
Yeah. So can you say your choice is the best one?
No, it depends on object. What do you want to do? So you have problem setting. So then you need to choose good convex function. So this is for example, in the case of quantum state family, you need to discuss this one. But sometimes depends on the situation, you need to change convex function. Even in the classical case, sometimes you need to change the convex function.
Okay, thank you. Any other questions, comments? So if not, let's thank the speaker again. Thank you very much. So the next talk will start at 3:20 in Japanese time and 2:20 in Chinese time. Yeah.
Okay, and now next chair is me. So please, sorry, I need to stop. So now I stop the screen sharing. So please, next speaker, prepare your screen sharing. So なんか間違えたな。
I can't hear nothing. What actually? Okay, can we get started?
Okay. 林先生、音声が聞こえないです。Hello, this is Shintaro Yanagida. 林先生 has some trouble on the mic, so let me start the next session. And the speaker is Professor Jun Yu Bai from SUSTEC, and the title is Strongly Fusion to Categories Group-like. So please start.
Okay, thanks for organizer for inviting me. Any comment or question will be welcome during my talk. I'm going to talk about strong fusion to categories group-like. This talk is based on the two-Josephson and Match-Lu's proof of the following result. If C is strong fusion to categories, then the equivalence classes of the incomposable objects of C form a finite group and the fusion product similar to Schur's lemma in one category. The equivalence relation is related by non-zero morphism. This result was first introduced and proved on physical level of rigor by Tianlan, Liang Kong, and Wen Xiaogang. The definition and the basic theory of semi-simple and multi-fusion two categories was first introduced in Douglas and Reuter's paper. Let's first review the main features. Let C be a complex number field. A two-category C is C-linear if all home sets of two morphisms are vector space over C, and both vertical composition and horizontal composition of two morphisms are bilinear. An object in a linear two-category is decomposable if it is equivalent to a direct sum of non-zero objects, and indecomposable if it is non-zero and not decomposable. A simple object X in two categories one such that any injected one morphism A2X is at zero or an equivalence. In fact, some simple two categories, all indecomposable objects are simple. I will use terms simple and incomposable interchangeably. In particular, the objects which we consider in a two category will only be sums of finite many simple objects. In our goal to define some simple two category, we present some definitions for the higher categorical generation of the notion of the idempotent complete. Two category C is locally idempotent complete if all objects AB in C, the home category home AB is idempotent complete. It is locally finite sum simple if home AB is furthermore a finite sum simple C linear category. That is a abelian C linear category with finitely many isomorphism classes of simple objects, and in which every object decomposes as a finite direct sum of simple objects. In what follows, we will see C is a local idempotent complete category. A condensation A condenses to B in a two categories C consists of the following data. There are two one morphisms F and G, two morphisms ipsilon and gamma, such that ipsilon compose gamma is equals to identity and B. A unit of condensation in a category C is a condensation equipped with the two morphism eta, such that F is a left joint to G. Let A be a single object in C monad P MU in two categories separable if there is that PP by more map C such that M compose C equals to identity P. Example for a separable monad is a separable monad in a two category with one object star is a separable algebra in E1 monoidal endomorphism category. A separable monad P MU is split if there is that unit of condensation, and G F is isomorphic to P. A two category C is two idempotent complete if it is locally idempotent complete and every separable monad splits. There is something different from the situation in one category. In one category, there is an equivalent of P squared equals to P, but there is no equality of locally idempotent complete. What? Is there any questions? I will go. I will go ahead. Galto and Theo Joseph-Reid develop a non-unit version of separable monad for two categories and showed that if C has a joint for one morphism, then the notion of two idempotent completes above and in the Joseph-Reid and Galto's paper will agree. A C-linear two category C is finite sum simple if it is finitely many isomorphism class of simple objects. It is locally finite sum simple. most important is it has the joints for all one morphism. So please remember this. I will use this repeatedly in the following proof. And has a direct sums of objects is two-idempotent complete. A multifusion two-category is finite some simple monoidal two-category in which all objects has dues. Let's recall that multifusion to one category case fusion means that if the endomorphism algebra is trivial, so there will be two reasonable categories of fusion when C is multifusion to category. We will focus on the strong generation case, which we will call strong fusion. It is to us that endomorphism one category is isomorphic to the WAC. That means the category of finite dimensional vector space. We now begin to develop the necessary graph calculus in order to prove the mean results. For an object x in C, we denote the integral x over s as wrapping of x around S1. This integral is a map. Note that it's map, not a functor. Because C is a two category, the looping of C is a one category. It's not a functor. In geometry, this means if there is a x sheet, we wrapping x into a cylinder. We now describe this operation algebraically because we are working with a strong fusion to category. Each object has due, and we have a unit. From tensor unit to the x tensor x due. Its corresponds to a half circle. The dashed line is the tensor unit. The dashed line is a tensor unit of C. From C to the x tensor x due. Also, since all the one morphisms as joints, there is a radial joint, eta x due from x tensor x due to from x tensor x due to the tensor unit. So if we compose these two, we will get the cylinder. We'll get a cylinder. Altogether, so we find an algebraic definition. The integral is equals to the eta x due circle eta x. There is an important theory which we call state operator correspondence. I won't give a proof in mathematics, but I will tell you how to understand the state operator correspondence in geometry. If we add elements E in the left, that's a point in the X sheet. Then we pinch this X sheet like this. The dashed line is the integral. That means every P will give away from the identity to the integral. So we have this equivalence. Away from identity to the integral is an element in the right. So every element in P will give a element in the right. So we have this equivalence. if C is still we can prove that if C is incomposable, then in the integral x, if x is incomposable, then integral x is a complex number. This means if we wiping x sheet, if x is a incomposable object, we wiping this x sheet, we will get nothing. So now we consider the tensor products of two incomposable objects. This presents a cylinder within a cylinder in the following. So if we wiping this two x sheets, we get this, a cylinder within a cylinder. Now that this is not equal to the two cylinders adjoined to each other. So we can say this map is not monoidal because a cylinder within a cylinder is not the same as the two adjoint cylinders. However, in the fusion, strong fusion case, if x and y are simple, then we make collapse down the linear cylinder, while the state operator maps into the vacuum. We may then collapse the outer cylinder. So we have the following corollary. In a strongly fusion two category, the tensor product of the incomposable objects is incomposable. Now we prove our final theorem. If C is a strong fusion two category, then the equivalence class of incomposable objects of C form a finite group and the fusion product. Similar to the Schur's lemma in one category, the equivalence relation is related by a non-zero morphism. If X is incomposable objects, then X2 is as well. And hence, so is X tensor X2. Since we have the co-unit eta X is non-zero, the incomposable objects tensor unit is isomorphic to X tensor X2. The identity in group is given by the tensor unit. The associativity is given by the associator of C. In the strong fusion two category, the tensor product of the incomposable objects is incomposable. So it is closed. Thus, the equivalence of the classes of the incomposable objects of C form a finite group and the fusion product. So I can finish.
Can you hear me?
Yeah.
So now I can share. So do you have any question or comment?
Can I ask a question?
Yes.
Yeah. Can you turn to page? I don't remember 7 or 8. There is a remark about the definition of condensation.
Definition of condensation.
Oh yeah. Maybe just a long remark. Yeah. So I'm not quite sure. While listening to your talk, what exactly are the two notions that you say is agree?
This notion is defined by the Douglas and Reuter's paper.
Which notion?
All this.
So these series of definitions you present to us, right?
Oh yeah.
Okay.
And the Galton and Johnson Fried define the non-unit version. We can see this notion is a unit. We have unit.
Yeah. Yes.
And Galton and Johnson Fried developed a non-unit version and show that if C has joints for all one of them, then the notion two idempotent complete in the Douglas and Reuters paper will agree with the notion of Galton and Johnson Fried's paper.
Okay, I see. Thank you.
You're welcome.
Yeah, may I ask a question?
Yeah.
Yeah, can you show us a slide of state operator correspondence?
Oh, yeah.
Yeah, is it a canonical correspondence?
What?
My impression is to make such correspondence. We have to take some ground state. Is it right or no? Ground state or vacuum. Oh yeah, it's my, of course it's my physical impression, but so your correspondence is canonically determined, or did you take some data such as ground state?
Yeah, it's canonical. The only structure, the only condition we need is multifusion two category C. If we have a multifusion two category C, we have this isomorphism.
So it's the only choice.
Yeah.
Okay, thank you.
Any other question or comment? So can I ask you,
Sorry, I have another question.
Oh, okay.
About this state operator correspondence. I remember that if X is an indecomposable object, then this integral of X over S1 is the complex number, right?
Yeah.
So when X is not indecomposable, what will the integral of X over S1 be like in general? Like what category or what set does it belong to?
It belongs to this set, to the looping of C.
Oh, okay.
We can see from
the
of
course.
Okay. X equals to the eta X circle or eta X. Eta X is from identity C, tensor unit to the X tensor X star. The eta X star is X tensor X star to the tensor unit. So we compose this we will get a map from tensor unit to the tensor unit.
Okay, so now you only suppose that C is multifusion. So omega C unit of C is not a very trivial category in general, right? Yeah, so the integral of X over S1 is in general not a very trivial object.
Yeah, in strong case, the looping of C is weak. So the identity tensor unit is a complex number.
Okay. Okay, I see. Thank you.
Other question or comment? I have one question. So could you give me some simple situation related to physics? Do you have some typical case related to physics? Physical object?
Oh, what? The
Can you
voice
hear me?
is low. It's so low.
No. Eh? Can you hear me?
Your voice is low. It's very low.
No. Can you hear me?
Oh yeah.
何やこれおかしいな。Can you hear me? So I have a question. So could you give me some physical situation related to physics? Some typical situation. Can you hear me?
Physics intuition.
Situation. The situation somehow a situation related to physics. What kind of a mathematical object related to physics? What kind of mathematical object related to physics?
Mathematical object related to the physics. Mathematical object. Your question is how to get a mathematical object related to the physics.
Yes.
In the 2D case, the object we can use fusion 2 category to describe it. In the 2D case, a physics system. For example, a torical model, we can use a fusion 2 category to describe it. The object is a domain wall, 1D domain wall in the torical model. There will be 6 1D domain wall in the torical model.
Domain wall.
Torical. You know torical model?
I don't know.
Sorry.
Can you write down in chat what model?
toric code model.
Toric code model.
Yeah. It seems this model is also famous in quantum information. Because this model is come from the quantum information theory. Torical.
I see.
So the object in the fusion 2 category corresponds to the torical model is the domain wall. There will be 6 domain wall in the torical model. So this corresponds to the 6 simple objects in the tori. Tori is a fusion 2 category corresponds to a torical model.
Domain wall. What is domain wall? Please write down. Domain wall.
Domain wall.
Domain wall. Okay. Okay, I understand. Okay, domain wall. Okay, thank you very much. Other questions?
All right.
So we don't have enough time. So thank you very much.
Oh yeah. Thank you.
So next, we want to proceed to the next. So Garholdis, Stavros Garholdis, from SASTEC International Center of Mathematics. Could you prepare your presentation slide?
Yes. Can you hear me?
Yes, yes. So please make a screen share first.
Let me try to share the screen and see if it works. If it doesn't, well, let me try to share. Do you see it?
Nothing now.
Yes, unfortunately, I had this problem with other things. So you have the slides of my talk. Maybe you can put the slides on and I just go through the slides then.
Okay. Wait. Okay, maybe you can see.
Yes, I can see. And you can hear me okay?
Yes.
Okay. All right. Can I start?
Yes, yes.
Okay. So I want to give you a historical introduction about the Jones polynomial of a knot, which was the birth and the reason for the existence of quantum topology. Maybe next slide. Yeah. So the Jones polynomial was discovered around 1983, about 40 years ago, in fact. When I give talks, I say that this is a new story, but it's already 40 years old. And it was discovered, in fact, not through topology, but it was discovered through a tower construction in von Neumann algebras. In fact, finite dimensional subfactors. And this tower construction led von Jones to realize that there is a representation of the braid group whose trace, because everything is a finite dimensional, so things have a trace, whose trace depended on a parameter called Q, and taking the trace, therefore, one gets a topological invariant, the Jones polynomial of a knot. So the origin is von Neumann algebras. However, once the polynomial was discovered, von Neumann algebras actually never came back to the game. So J is a polynomial of knots or links. A knot is an embedded circle in 3 space, and a link is an embedded union of circles in 3 space. These embeddings are considered modulo isotopy, that is, you're allowed to move the knot a little bit or the link as long as it does not cross itself. Because of that, there are only countably many knots and links, although it is hard to list them because it's hard to find a criteria of what is when is a knot simpler than another. Okay, so to a knot or a link, the Jones polynomial is a Laurent polynomial, that is a polynomial in Q, actually technically Q to the 1/2, or Q to the -1/2 with integer coefficients. As an example, I list the Jones polynomial for the 3 perhaps simplest knots in any table of knots. There's only one knot with no crossings, the unknot, for which the Jones polynomial is 1, normalized to be 1. The next one is the trefoil, the only knot with 3 crossings. And below it is the figure 8 knot, the simplest hyperbolic knot, and you can see the polynomial. The rule for the Jones polynomial is a linear system of equations. So every time you have a planar projection of a knot and you choose a crossing, which I have put in red. So to a crossing, you can do 3 things. You can either change the crossing or smoothen the crossing, and that gives a linear system of equations for the Jones polynomial with one initial condition, namely Jones of the knot is 1. Maybe next slide. Yes. So for example, suppose you wanted to calculate the Jones polynomial for the trefoil. You choose any crossing you want, and the 2 blue arrows mean that if you change the crossing the way I show, then the Jones polynomial of the top is a linear combination of the 2 Jones polynomials of the bottom. So this is like a chain reaction, you know, like uranium atoms and stuff. All right, so if you go now on the left blue arrow, you see that the knot that you get simplifies. It actually becomes eventually the knot. If you follow the right blue arrow, on the other hand, it's still simpler because the original knot had 3 crossings, but the new one has only 2. And now if you choose any other crossing of this so-called Hopf link, you can create 2 new blue arrows, for one of which will give you an unlink with 2 components, and the other one will give you the knot. So you can reduce the computation of the trefoil, or any knot in fact, to the computation of the Jones polynomial of the knot using a linear system of equations. Now, I only gave you one initial condition, namely the value of the knot, but I didn't give you the value of the unlink with 2 components. So is this a free parameter or not? Well, every physicist knows that infinity minus infinity is actually 0, double 0 actually. You can go to the next page. So if you apply this formula that looks very silly, and you use the fact that both infinities are in fact the knot, you find out that the Jones polynomial of the unlink of 2 components is q minus q inverse divided by q to the 1/2 minus q to the minus 1/2. This is a rational function of q because it has a numerator and denominator, but conveniently the denominator divides the numerator, and what you get is q to the 1/2 plus q to the minus 1/2. There is a special value for the Jones polynomial, namely what happens when q is equal to 1. When q is equal to 1, there is no difference between a positive and a negative crossing, so therefore topology evaporates. If you study knot theory, but you allow to change any crossing you wish, then all the knots become the knot and all the links become the unlink. And in this case, the Jones polynomial of a knot is 1, and the Jones polynomial of a link with at most 2 components, it is 0. So as soon as the Jones polynomial was invented by von Jones, very soon, months later, it was realized by the Russian school, Kirillov, Reshetkin, Turaev, Drinfeld, and others, as well as the Japanese school, Jimbo, Miwa, and many more researchers, that the underlying symmetry was that of a Lie algebra, more precisely a quantum group, so a deformed Lie algebra. And it was realized that the Jones polynomial is actually the simplest example of a simple Lie algebra, namely SL2, in its fundamental representation. SL2 being 2 by 2 matrix is A, B, C, D with complex entries and trace 0. And 2 by 2 matrices act on C2 just the way that the 2 by 2 matrix acts on a scalar, on a vector, 2 by 1 vector. They form a Lie algebra. SL2 is a Lie algebra. However, there are more representations of the SL2 Lie algebra. Namely, there is one for dimension n called the n-dimensional representation. You can think of it as the space of homogeneous polynomials in two variables of degree n-1, where SL2 acts on x and y. Maybe next slide.
Can I have a question? Sorry.
Yes.
So you have said that the Jones polynomial is a simplest example of Lie algebra. I don't know in what sense is this Jones polynomial related to Lie algebra?
So the representation theory of a Lie algebra of a quantum group using a representation of it gives you an R matrix, which gives you a representation of the braid group whose trace is a polynomial invariant. And if you did that for SL2 in the defining representation, you get the Jones polynomial.
Okay.
It's a long answer. It's not a straightforward, and certainly not an answer that is related to the linear system of equations that I told you about. Yeah. So because C to the n, you can think of it as the symmetric power of C2, therefore there exists, I mean, according to quantum groups, a Color-Jones polynomial, which is not one polynomial, but it is one polynomial for every capital N being 1, 2, 3, and so on. If capital N is 1, this is called the vacuum, then the Color-Jones polynomial of any node is 1. If capital N is 2, then we're talking about the defining representation, in which case the Color-Jones polynomial, when capital N is 2, is just the Jones. And what is it for capital N is equal to 3? Roughly speaking, it is the Jones polynomial of the 2 parallel of the knot. I try to draw the 2 parallel of a trefoil. You have to be careful, plus the Jones polynomial of the empty knot with some coefficients. You have to be careful when you draw the 2 parallel, because you have to draw it with something called the zero framing to cancel some anomaly. But the representation wise, you take the fundamental representation C2 and its tensor product with itself, and you decompose it as a irreducible representation of the Lie algebra. So it's a 4-dimensional space, but it decomposes as C3 plus C, and it is this decomposition that is responsible for the formulas or the definition, if you wish, of the Color-Jones polynomial. Okay, now you may ask, isn't the Jones polynomial of a node strong enough? Why should I care about the Color-Jones polynomial, which is not one, but it is a whole sequence of polynomials? I will tell you the answer to this question a little later. Let me just say now that accidents can happen if you have just capital N equal 2. But before I tell you the answer, let me give you an example of the Color-Jones polynomial of the figure 8 knot. It is a finite sum, a one-dimensional sum, and the summand involves Pochhammer symbols or quantum factorials. In general, if you follow the representation theory of quantum groups, you're going to find similar formulas, terminating formulas, finite formulas for all nodes or links colored with any representation, except that there will be in quantum factorials in the numerator and denominator, something like quantum binomials and a multidimensional product and more complicated. But that's the shape of the answer of how do these polynomials look like. Maybe next page. Okay, so the next part of this story was Witten in 1989, who invented or introduced rather the Chern-Simons path integral. The history is the following. Atiyah, Witten, and Donaldson were in a conference in Oxford, and they went for a little weekend trip to Swansea by the sea in England. And Atiyah asked Witten for a relation between the SU2 Jones polynomial. So I did say SL2 before, but Atiyah, I mean, being more of a geometer, he replaced the Lie algebra by the Lie group. So he knew that the Jones polynomial has something to do with the compact Lie group SU2. And he knew that his student Donaldson had just proven amazing theorems in the world of smooth form manifolds using the anti-self-dual equations of Yang-Mills theory, which is an SU2 theory, an SU2 non-abelian gauge theory. So Atiyah asked, what is the relation between the three-dimensional Jones polynomial and the four-dimensional Yang-Mills? Yang-Mills is a metric-dependent theory, whereas the Jones polynomial is a topological. So Witten's response was, well, if you dimensionally reduce Yang-Mills, which means your four manifold is three manifold cross the real numbers, and you write down the equations, then the Yang-Mills action becomes the Chern-Simons action, which I have written in the bottom of the page. It says CS of A is equal to the integral over S3 of trace of A wedge A plus 2/3 A wedge A wedge A. So Witten knew that. And right away, you know, he said, okay, the answer to Atiyah's question is that the Jones polynomial is evaluated at roots of unity. Oh, I don't know what happened to the denominator. It's e to the 2 pi I over k, and it should be e to the 2 pi I times k. I'm sorry about that. Something stupid happened on my transparencies. So the Jones polynomial, the color Jones polynomial evaluated at a root of unity is written as a path integral. What are you integrating? You're integrating over the affine space of SU2 valued one forms on the three sphere. So the space of one forms on the three sphere is infinite dimensional. The SU2 valued is basically three copies equally infinite dimensional. And if you have a knot, you can look at the holonomy along the knot of a connection. So when you go around the knot, the connection does not come back to itself. That's the issue of the holonomy. You take the trace and to make a number, and you integrate or you average over all connections. And the Chern-Simons function, so this A that I tell you in the argument of Chern-Simons is basically a one form with values in some Lie group or Lie algebra. So therefore, dA is a two form, A wedge dA is a three form. Because it's matrix valued, the trace is just a three form. You integrate a three form over three sphere, you get a number, and that's the Chern-Simons. That is the only thing that's well defined in this integral. The rest of it is, well, I mean, the rest of it is topological quantum field theory. So Witten filled a stack of napkins, about 20 I heard, and he has kept these napkins. I have not seen them myself, but I have seen pictures of. And the paper was produced the next day in typical Witten fashion. Okay, we can move on.
Next one.
Yeah. Next. Yes. Okay. So further developments after Witten. So after Witten, one can talk about the asymptotic expansion of Chern-Simons theory at a critical point of Chern-Simons action. So the critical points are flat connections. Among the flat connections, there is the trivial flat connection, which is actually the most non-trivial one. The asymptotic expansion led to what is now known as Vassiliev or finite type invariance. That is still early 90s. For instance, if you took the 10th derivative of the Color-Jones polynomial at q equal 1, you're going to find a polynomial of capital N of degree 10, whose coefficients, they satisfy some difference equations at 11 random points of the knot. Shortly afterwards, Drinfeld and Kontsevich both got the Fields medal at the same time with Witten, constructed the universal Vassiliev invariant, as well as a representation in non-abelian algebraic geometry of the Galois group of algebraic numbers over Q, this absolute profinite group, which is very difficult to understand. Okay, now there is a relation between the Jones polynomial and the Alexander polynomial, and the Alexander polynomial is a classical knot invariant because the Alexander polynomial basically determines the homology of the universal abelian cover of a knot. So the Alexander polynomial was known since 1920s about, and it was discovered by Conway in the 70s that the Alexander polynomial has this a similar recursion like the Color-Jones. The only thing that it is missing is the multiplication by t and by t inverse on the left-hand side at the analogous crossings. Okay, so if we therefore write the Color-Jones polynomial, replacing q by exponential of h being Planck's constant, and keeping n as a variable, so then we get a formal power series in two variables, capital N and capital H. These the exponents are arranged in a triangular fashion. So the power of capital N is always less than or equal to the power of capital H. And then we can, therefore, these Aij are finite type invariants of degree j. So if we sum these infinitely many finite type invariants just on the diagonal, which is still determined by the Color-Jones, and we sum them up, what we find out is that this is in fact not a polynomial, but the inverse of a polynomial. In fact, it's the inverse of the Alexander polynomial. So that was a paper of Barnatan and ourselves in 1995, and showed the first relation between perturbation theory of Chern-Simons and not the trivial connection, but the abelian connection. Okay, we can move on. Next page. A little before us and completely unknown to the relation between the Jones polynomial and the Alexander was a work of Kashaev in 1994, at that time in Russia, who formulated the volume conjecture. So what does the volume conjecture say? I wrote it in red. It says that the growth rate of the nth Color-Jones polynomial at the nth root of unity, so Planck's constant goes to 0 and color goes to infinity in such a way that the product of Planck's constant 1 over n times color n is equal to 1. In that limit, the Color-Jones polynomial grows exponentially, and the exponential growth rate is the volume of the knot divided by 2 pi. I forgot the 2 pi. What is the volume of a knot? So, according to Thurston, every 3 manifold can be decomposed in one of 6 or 7 geometries, namely constant curvature special geometries. Among those is the hyperbolic geometry. So typically, a random 3 manifold is hyperbolic. A knot complement is a non-compact manifold, but it is hyperbolic and it has a unique metric by Mostov. And because the metric is unique and therefore rigid, the volume with respect to that metric is a topological invariant. Now, the volume might be infinity because it's a non-compact hyperbolic manifold, However, it is not infinity, it is finite, and in fact a very interesting number. For the example of the figure 8 knot, I gave you before the formula for the Color-Jones polynomial. Now I give you a formula for the Kashraev invariant, which becomes somewhat simpler. And it grows according to the volume of figure 8 times n divided by 2 pi. And the volume of the figure 8 is 2 times the imaginary part of the dilogarithm at 2 pi I over 6. Dilogarithm of x is the sum of x to the n over n squared. And logarithm is basically the sum of x to the n over n, except as logarithm of 1 minus x. Next page. Okay, so according to Thurston, the complement of the figure 8 knot can be decomposed into two ideal tetrahedra. These are combinatorial data. And the hyperbolic metric is given by putting a specific so-called shape to this ideal tetrahedra, in this case, a sixth root of unity. So for every knot has some combinatorial information according to Thurston. It can be ideally triangulated. And if you solve some nonlinear equations related to this triangulation, you can actually recover the hyperbolic metric. So you can recover a solution to the Einstein equation by solving systems of polynomial equations. And therefore, you can find the formula for the volume. Now, if you want to get the Fields medal, you can try to prove that the volume of the figure 8 is irrational. I'm sure if you manage to prove this, you'll be able to prove a few other things, and that is a Fields medal problem. Okay, we can move to the next page. Q-difference equation. So the sequence of Color-Jones polynomial is not a random sequence of polynomials if you fix your knot. What I mean by not random means that it satisfies a linear recursion relation. That was found out in 2005 in joint work with Tang Le. So for instance, for the figure 8 knot, the recursion relation is actually quite complicated to write down. So I'm telling you the shape for the figure 8 knot. So the shape is the following. So you take the Color-Jones polynomial at n plus 2. You multiply it by a2, and then you do a at n plus 1. You multiply by a1 and at a0, and then there is a right-hand side, where a0, a1, and a2 are Laurent polynomials in two variables. But we specialize one of the variables to be q and the other to be q to the n. And you can actually write the recursion in operator form. So there is an operator L, which shifts a sequence Jn, one to the right. And there is an operator M, which multiplies J sub n by q to the n. The two operators n and m do not commute, they q commute. And therefore, the Color-Jones polynomial is annihilated by a polynomial operator in L and M. And the conjecture, this AJ conjecture, is that if you put q equals 1, so therefore the operators now L and M commute, then this polynomial defines the moduli space of SL2 representations of the knot complement. I should say one word about why the Color-Jones polynomial is satisfies a recursion. So I had asked around that time, around 2004, Doron Zeilberger, who is an expert on, he invented Q-holonomic sequences and invented them in order to prove automatically and by computer every multinomial identity that you can imagine. So I asked Zeilberger, well, I wanted to prove that the Color-Jones polynomial is has such a recursion, you know, and he said, well, do you have a formula for the Color-Jones? And I said, yeah, I do, but it's complicated. It's a finite, you know, it's a finite dimensional sum and involves signs and powers of Q and Q binomials. You know, he said, well, is that all? You know, he said, doesn't involve anything else. I said, no, but it's a complicated formula, you know. And he said, well, then it's trivial. And the reason it is trivial is because his fundamental theorem is that every multidimensional sum of a Q hypergeometric summand is always Q holonomic. So you get these recursions for free. Now, the thing that wasn't as trivial, so that actually proves right away that the Color-Jones polynomial satisfies a recursion. If you wanted to do it for other simply algebras and other representations, it's a little more complicated, and you can use the representation theory of quantum groups to actually factorize the R matrix and do it in general. But the main idea is every formula you write, even if you made a mistake, it will satisfy a recursion. We can move next. Okay, so here are a few other things that you may extract from the Color-Jones polynomial. So suppose you only were interested, these polynomials, because they satisfy a recursion, like quantum n factorial satisfies a recursion, and therefore if you were to expand quantum n factorial, you would find out about that it has about n many terms. The number of terms is growing linearly in n, but the powers of these terms grow quadratically and the coefficients grow factorially, in fact. So if you wanted to extract one number out of the Color-Jones polynomial, perhaps you want to extract the degree. Okay, and if you look in the degree, so the degree, the theorem is a little later, is that it is a quadratic quasi-polynomial. What does that mean? I give you an example. For the -237 pretzel knot, you can see 2 half twists left-handed and 3 right-handed and 7 right-handed. That's the famous knot, pretzel knot. So for this example, it is the integer part of 37/8 n squared and 17n, which means that it is actually about, it is exactly that plus a little correction epsilon of n, but the correction takes constant values when n is 0, 1, 2, or 3, modular 4. Okay, so in fact, we proved that every sequence of polynomials or rational functions that satisfies a linear recursion has degree, which is quadratic quasi-polynomial. Now, let me say something. If out of a polynomial in Q, you extract the degree, that basically says that a Q square is so much bigger than Q. In other words, you're looking at the limit of the polynomial as Q goes to infinity. If you keep in mind that Q is exponential of H being Planck's constant, the limit Q goes to infinity is the limit where Planck's constant goes to infinity. So this is the opposite of semi-classical expansion. So this is the strongly coupled regime, if you wish. This is the tropical limit. In mathematics, it's called the tropical limit. And the tropical limit is actually quite nice. I mean, it's a quadratic polynomial. And we also have a conjecture for what is the quadratic coefficient, this 37/8. I was asking around what could 37/8 be in relation to -237 pretzel, and eventually I found an answer in the form of a conjecture, which we now know. I had shown the conjecture for alternating knots and torus knots, and now we know it for many more classes of knots. Basically, it's a slope conjecture that tells you that this 37/2, it's the slope of an incompressible surface in the knot complement. So something that relates to classical topology. So the tropical limit, Q goes to infinity, apparently it relates to not hyperbolic geometry anymore, but classical topology. We can go to the next page. Okay, so this is, I believe, this is kind of essentially my last page. Yes. So in the last 5 years, there have been many more developments. For instance, there have been invariants of knots that are not polynomial, that have been defined by physicists and mathematicians. I'll give you a list of them. One is a supersymmetric 3D index defined by Timofte, Gayotto, and Gugov, and also redefined by ourselves, as well as interpreted as a meromorphic function. We work with Rinat Kashaev. Another is a family of invariants called state integrals. These have to do, so these are analytic functions which are not invariants, and they're holomorphic functions on the complex numbers minus the non-positive real numbers, including 0. So these state integrals are related to what's called the quantum Teichmüller theory. So it is a Teichmüller theory that does not have corresponding quantum groups, and it deals with representations which depend on continuous parameters and leads to representations of braid groups. But these representations in braid groups, they are now defined on Hilbert spaces, typically L2 of R. That may actually be interesting for quantum computation, perhaps. And the building block of the state integrals is a famous special function, the Fadeev quantum dilogarithm. A third class of invariants are some factorially divergent formal power series, which appear in the asymptotics, for instance, of the Kashaev invariant and in the volume conjecture. These series have been defined, introduced by Timofte and ourselves, and also ourselves and Ton Zaghir. All these papers are in the archive, but I don't want to give too many references for that. I can tell you if you want. But let me just give you a toy example, because I've been giving you the example of a theory for the figure-8 knot. So, for instance, for the figure-8 knot, all these invariants that I mentioned before, 3D index state integrals, and these series, they are related to these Q-Hebel geometric series. They are now not terminating. They're power series in Q. You can expand them around Q equals 0, and you're going to find integer coefficient, interesting integers, which are supposed to count BPS states of some supersymmetric theory. And this is the current state. The interpretation of these integers is still geometrically unknown, but they have to do with versions of Khovanov homology or brain counting. So basically homological chain complex constructions in 3 or 4 dimensions, and are not understood yet. Maybe my next slide. Thank you very much for your attention.
No, thank you very much. So do you have any question or comment?
Yes, may I ask a question?
Of course.
Yeah, so your talk is restricted to three-dimensional case.
Yes.
How about the possibility of other dimensions? You briefly mentioned four-dimensional theory, like Donaldson.
Yes.
How about
Yes. Yes.
how do you think about the extending your story to other dimensions?
Okay, so first there is an extension in 3+1 dimensions of Witten, actually Witten and Heidi.
Three dimension. This one.
3+1. So this is a 2+1. Yes, so the theory I described is 2+1. There is an extension to 3+1, which involves the Khovanov homology. So there is an extension of Khovanov homology for knots in any three manifold, you know, except that there is no Jones polynomial of a knot in a three manifold, but there is a Q series. So not a polynomial, but a whole power series. And Witten has defined the theory in 3+1 dimensions to calculate the version of this Khovanov homology. What is the problem? These theories tend to depend on the metric. So for instance, Yang-Mills theory in four dimensions uses a tricky assumption that B2 plus is greater than 1 or greater than or equal to 1. And if B plus is 0, then the theory is actually metric dependent. So the proposals actually of Witten and Kapustin in 3+1 dimensions are no longer topological. They depend a little bit on the metric, but worse than that, they are not exactly solvable. Exactly solvable means that you have a topological quantum field theory where you know all the constants of all representations of R matrices, of all fusion rules, of all canonical bases in these representations. You don't even have a sign ambiguity. And in this case, yes, you can compute the theory in any knot or any three manifold. Unfortunately, the Kapustin-Witten theory requires solutions. I mean, so there are chain complexes whose boundary maps depend on Euler characteristics of moduli spaces of some points on the manifold. And those moduli spaces are not known, and their Euler characteristics are very difficult to compute. So their theory exists, but not in a computable fashion. Now, Witten has a further extension of this theory into 4+1. So in total, a 5-dimensional theory. However, the number of supersymmetries is maximal there, and therefore this extension of ideas will runs out of supersymmetry, and it does not even go up to 6 dimensions like Calabi-Yau's. So therefore the theory ends in 5.
Okay, thank you very much.
Oh, thank you very much. Other question? Anshibai, so please, Anshibai.
Yes.
No? So okay.
Can I ask a question?
Okay, please.
Sorry. I have a rather trivial question that there is. I'm sure that there is definition for knot, but you seem to suggest that it is hard to distinguish two knot. So my question is, can't we just use definition of knot to distinguish two knots?
Okay, that's a great question. So first of all, I should say that the Color-Jones polynomial does not distinguish mutants. Mutants means you take a portion of a disk that intersects the knot in 4 points, you rotate and glue it back. So the most famous example of mutant knots is the Kinoshita-Terasaka and Conway-mutant pair of 11 crossings. So the colored Jones does not. However, the colored SU3 Jones polynomial does. And conjecturally, the colored SUN Humphrey polynomial already distinguishes knots. What is the problem? Well, if you do all SUN and all colors, so a representation of SUN for arbitrary n is basically a partition. So there are not finitely, I mean, the space of partitions is not even parameterized by finitely many parameters, because partitions can have arbitrary number of rows, and within these rows, arbitrary length. So partitions are functions of infinitely many variables. So conjecturally, the colored Humphrey polynomial, as it is called, distinguishes knots. But if we really want to distinguish knots, well, so I said that, but it's also true that even the Jones polynomial itself, for a knot with maybe 150 crossings, is difficult to compute, and in fact, it's a sharp NP problem to even compute the value of the Jones polynomial on the fifth root of unity. That's a universal Sharpie actually complete problem. So if you want to use these quantum invariants to distinguish knots, the answer is that they are not really suitable for this. But there is something which is suitable, namely hyperbolic geometry. So if you compute the 4-domain of a knot, which actually can be done, compute numerically, which can be done for knots with 150 crossings in this program called SNAPPy of Jeff Weeks, Nathan Dunfield, and Mark Kuhler. So if you do that, you can easily distinguish not just Kinoshita-Terasaka, but you can distinguish knots with 150 crossings easily, and numerically verifiable. So it depends what you want. Of course, you can also distinguish a knot by just a presentation of the Van Noy group and the peripheral system. There is a theorem that if you gave me the Van Noy group and the long meridian, that by itself, up to isomorphism, uniquely determines the knot. But this is highly non-abelian information. And of course, then there is the absolute invariant of a knot, which is like, it's the delta function, like the delta function of Kinoshita-Terasaka is 1 if the knot is Kinoshita-Terasaka, and 0 otherwise. Those delta functions also distinguish knots, but not in a useful way.
Okay. Thank you.
Thank you very much.
Thank you.
Other question? Other question or comment? So I have one more question. You consider Eisenstein series. So if possible, I want to know the relationship with between the Eisenstein series and the Eisenstein ring. This is completely different object. There is no relation. Or
I'm sorry. There is a feedback on the sound.
I see. So I want to know the relationship between the Eisenstein series and Eisenstein ring.
Oh, Eisenstein ring.
Yeah.
So you refer to this weight 1 Eisenstein series?
Yes, and ring, Eisenstein ring.
Oh, Eisenstein ring, I don't know, but the modular.
Maybe no relation. Maybe no relation. Okay.
You mean modular forms which form a ring are generated by Eisenstein series E4 and E6. This is an exceptional Eisenstein series. which is actually not modular.
Maybe modulo 7, not 6.
E4 and E6, I think.
6.
Mhm.
But I think Eisenstein ring is related to the modulo 7.
Oh.
Maybe different thing. Sorry.
I'm partially losing the sound, but we can discuss it further on chat or later. I do hear, yeah,
Yes,
some,
of course.
yeah. Yeah. Other questions?
Okay, so I'm afraid Masahito has some problem with Zoom. So are there any questions? Okay.
Thank you.
So if not, let's thank that speaker again. Thank you very much. Nice talk.
Thank you.
Okay, and now
林さん、大丈夫ですか？なんかちょっとズームの調子があまり。
いや、もうダメですよね、これ。でおるとダメですわ、もう。休みの日は出勤せんといかんですね。sorry, we have a trouble. So because now today is holiday. So in the case of holiday, usually I stay in my home. But in the case of holiday, internet connection in my home is not so good. So
you are at your home. So
Yeah,
so the internet connection is not so good.
not so good. Maybe in office much better. So
Yeah, I see.
so anyway, so now we go to the next speaker. So next speaker is Jiahe Zhao from Chinese Academy of Science. The title, please prepare your slide. So please make share. Jiahe Zhao.
Okay, could you hear me?
Yes, of course.
Okay, then should I share my slide now?
Yes, please.
Okay, could you see my screen?
Yes, of course.
Well, first, I'd like to thank the organizers for inviting me to the workshop. The title of my talk is Generalized Edinburgh-Waltz Calculus and the 1D Condensation Theory. In this talk, I'll develop a kind of Edinburgh-Waltz calculus for modular categories over finite tensor categories. To do this, I will introduce the notion of modular ends or coends. Okay, then I'll apply these mathematical notions to the condensation theory of one-dimensional topological order. In particular, I will explain the geometric construction of the 1D condensable algebra. First, I'll fix some notations. We fix K to be an algebraically closed field of characteristic 0. We use VAC to denote the category of finite dimensional vector spaces over K and K linear maps. All categories we use are finite categories over K, which means they are categories equivalent to the category of finite dimensional modulus over some finite dimensional K algebra. by a finite tensor category C, we mean a finite monoidal rigid category whose tensor unit is simple. For an algebra A in C, we use R mod AC, or respectively R mod AC, to denote the category of right A modulus in C or left A modulus in C. For two algebras A and B in C, we use bi mod AB to denote the category of AB bimodulus in C. For simplicity, when C is equal to VEC, we simply use the notation R mod A or R mod B bi mod AB. Okay, similarly. If C is a finite tensor category and Mn are finite left C modulus, we use this notation to denote the category of right exact C modular functors from M to N, or respectively, we use this notation to denote the left exact functors. Okay, any question is welcome. Then I'll introduce classical Morita theory. Classical Morita theory studies the following problem. Given two finite dimensional K algebras A and B.
Wait. So Morita is some Japanese guy. Could you say the full name of that Morita? Because Morita is very common name in Japan. So we can identify which Morita.
Well, are you asking me the full name of Morita?
Yes.
Well, maybe I don't know.
Someone knows that which kind of Morita? Maybe somehow related to algebra.
Okay. Maybe I'll check it after the talk.
Okay.
Okay. Given two finite dimensional K algebras A and B, when do we have an equivalence of K linear categories from R mod A to R mod B? Okay. This problem is now well understood by the famous Edinburgh-Watts theorem. The theorem states that for two finite dimensional K algebras AB, there is a canonical equivalence of categories between the category of AB bimodulus and the category of K linear functors, right exact K linear functors from R mod A to R mod B. Okay. In particular, equivalences between R mod A and R mod B are classified by invertible AB bimodulus. Moreover, the equivalence in the Edinburgh-Watts theorem can be constructed explicitly as follows. We can construct the two functors phi and psi. Here, phi is a functor from bimodulus to the functor category, which sends a AB bimodular M to the tensor product functor. Okay, you see the tensor product functor will send a right A modular to a right B modular, right? And psi is a functor which sends the functor F to the image FA. And here FA is canonically equipped with AB bimodular structure. So it will lie in the category bimod AB. And it is direct to check that phi and psi are inverse to each other. Here we'll give a remark that we also have a dual version of Edinburgh-Watts theorem, which establishes an equivalence as follows. It is an equivalence between the bimodular category and the category of left exact functors. Okay. Now we want to develop a coordinate-free version of Edinburgh-Watts theorem. Okay, I'll explain the meaning of coordinate-free. To be explicit, for two finite categories Mn, we want to find the following equivalence between M of box times N and the category of right exact functors from M to N. To solve this problem, we can find algebras A and B such that R mod A is equivalent to M and R mod B is equivalent to N. And then under these coordinates A and B, we can identify the tensor product with the bimodular category. Okay, and then we use Edinburgh-Watts theorem. We get the desired equivalence. However, the choices of A and B are not canonical, and neither is the identification M of times n and the bimodular category. And what we really want is a coordinate-free version of Ehrenberg-Waltz theorem. Okay, to do this, we need to review the notion of ends and coends. Let f be a functor from C of times C to D, and let delta be the diagonal functor, which sends each object in D to the corresponding constant functor. The end of f is a pair. Okay, the pair consists of an integral. Well, it is an object in D, and I use this integral notation. Okay, and the pi is a dinatural transformation from the constant functor to f, such that they are universal in the following sense. If I take another pair, A alpha in this comma category, okay, then there is a unique morphism from A to the integral, rendering the whole diagram commutative. Okay, we can look at this diagram. This integral is equipped with the projections from each component fxx and fyy, and this diagram is commutative. And if I have another A equipped with the projections alpha x and alpha y, then I can get the unique morphism alpha tilde, rendering the whole diagram commutative. The notion of a coend is defined duly. Let's see a few examples of ends and coends. Let's C and D be categories and Fg be two functors from C to D. Then the set of natural transformations from F to G can be represented as such an integral. Okay. The second example is called Yoneda or co-Yoneda lemma. For each functor K from C to D, we have the following isomorphisms of functors. Okay. Yeah, and here this bullet means the canonical action of VAC over a linear category. Okay, now using the language of ends and coends, we can write down the coordinate-free version of Ehrenberg-Waltz theorem as follows. The theorem states that let CD be finite categories, then there are two pairs of the joint equivalencies of categories. Well, we have a functor phi L. It sends this tensor product to this functor. Okay, and its reverse is given by psi L, which sends a functor from C to D to such a coend. Okay, and similarly we have this pair, phi R and psi R. Phi R will send the this tensor product to such a functor, and phi R will send a functor to this end. It is easy to check that they are the joint equivalencies. Okay, now we want to propose some generalizations towards the C modular case. For now, we have been discussing finite categories, that is modular categories over VAC. And from now on, we turn to study the Morita theory of finite modular categories over some finite tensor category C. If M is a C modular, then we may equip M op with different right C modular structures using the rigidity of C. For example, we use M op L to denote the right C modular equipped with the following action. The action is defined as follows. M O.LC is defined to be the left action of C left dual over M. Okay, and we use M of R to denote the right C modular equipped with the following action, which is similar to the above construction, but here we use the right dual. Okay. Now we formulate a theorem of Cohen and Zhen. let C be a finite tensor category and Mn be finite left C modulus. Then there are equivalencies of categories. The phi r is a functor which from the relative tensor product from this to this tensor category to this functor category, right? It sends a tensor product to this functor. Okay, and dually we can we have phi L. It is defined similarly. You can see that these two functors is quite similar to the k-linear case, right? We may understand this theorem by taking coordinates. As a matter of fact, we can always find algebras AB in C, such that M is equivalent to R mod AC and N is equivalent to R mod BC as left C modulus. Under these coordinates, we can write down the equivalence phi R explicitly. If we take the coordinates right, then the left-hand side will become the category of bimodulus, AB bimodulus in C, and the right-hand side become this. And under these coordinates, the functor phi R will send a bimodular M to the tensor product functor, which is completely parallel to the k-linear theory. Okay. The problem is that we cannot write down the quasi-inverse of phi L and phi R in the coordinate free form. To solve this problem, we need to introduce some new constructions. Here is a new definition. Let C be a finite tensor category and M be a left C modulo. And then we may equip M op with the right C modulo structure M of L. Let Fe be a functor from M of L times M to D be a balanced C modulo functor, with E being the balancing natural isomorphism. The C modulo N of F is a pair. Well, the pair consists of an object in D, which we denote by such an integral with a C label. Okay, and pi is a dinatural transformation from the constant functor to F. But moreover, we require the following diagram to be commutative. Okay, let's look at this diagram. The pi m and the pi m is the projection to the M factor, and a pi CL dot M is the projection to the CL dot M factor. I'll explain what these two arrows are. This arrow is given by E. E is a balancing natural isomorphism. Okay, and we take the this component. Well, this arrow is given by the co-evaluation map of C. Okay, so the CO dot CL emerge in front of M, and we require the pair to be terminal among all such pairs. Okay, so it is some kind of limit. Okay, then I'll introduce. I'll explain this new construction. Okay, first, the notion of a C modular coend is defined dually, which we denote by such a integral. The two constructions should be regarded as some kind of modified end and coend, which is compatible with the rigidity structure of C. Their power shall be illustrated by the following examples. The first example is that let Mn be left C modulus and let Fg be C modular functors. Here, the eta F and eta G are the C modular structures. Okay. Then we have such an isomorphism. Okay, if you do the C modular integral, you take the end, and you will get this set. Okay, the right hand side means the space of C modular natural transformations. Okay, note that the functor, this functor from M of L times M to VAC is equipped with a canonical balancing structure. For the second example, it is a generalization of the unida and co-unit lemma in the k-linear case. Okay, let G and eta G be a C modular functor. And then there are canonical isomorphisms of C modular functors as follows. Okay, you can compare it with the unida and co-unit lemma in the k-linear case, and they will look exactly the same. The second example, the third example, for two finite tensor categories CD, we say that they are Morita equivalent if they can be connected by an invertible bimodular M, or equivalently if there is a bimodular M such that the monoidal functor U from D reverse to the functor category is an equivalence. And now we may use the language of C modular N to write down the quasi-inverse of U. As a matter of fact, we compute its right adjoint UR, which reads, okay, UR is the functor from the functor category to D reverse, and which send F to this integral. Okay. So using the notion of C modular ends and coends, we can finally write down the generalized form of Ehrenberg-Watts calculus. Let C be a finite tensor category and Mn be finite left C modulus. Okay, then there are adjoint pairs of equivalences. Okay, the functors phi L and phi R, we have introduced them, and now we can write down their quasi-inverses, which are given by psi L and psi R. Psi R will send F to such integration, and psi R will send F to this integration. Okay. Okay. Finally, I will introduce some physical applications. In physics, 1D gapped topological order is described by a unitary fusion category, which is a special case of a finite tensor category. So our construction can apply to it. Okay, we'll explain the geometric construction of 1D condensable algebras. Let CD be Morita equivalent 1D topological orders separated by a zero-dimensional domain wall. Here, the small m is a distinguished object in M, and M is a CD bimodular. Then C and D can condense to each other. The condensation process from D to C is controlled by a distinguished object in D, which is called the condensable algebra. Okay, for details, you may see the reference. Intuitively, the condensable algebra, which condenses D to C, can be obtained by conducting a dimensional reduction process to a C bubble in D. Okay, we can look at the picture. Here, the two sides are 1D D phase. Okay, they are D phase and they are one-dimensional. And in the middle, we have a C phase. Okay, and they are separated by, here we separated by the M is a domain wall. Okay, and M of is the inverse domain wall of M. And we claim that the condensable algebra is obtained by we squeeze this C phase to a zero-dimensional defect, which we denote by A here. Okay. Okay, then we can now show that the condensable algebra is exactly given by the internal form. Okay, MM in D reverse. Okay. How to compute it? Well, it is computed by the composition of the following equivalences, right? The first equivalence is given by we send this tensor product to this functor. Okay, and then we use the previous examples to compute it, and finally we get the internal form. I will not explain the details of the computation. Okay. That will be all my talk. Thank you.
Thank you very much. So any question or comment? Yeah.
Sorry.
Somebody question?
Is there any questions?
So I'm slightly surprised. So there are so many Japanese names.
Yeah, like Morita, Yoneda.
Yes, but unfortunately, they are not related to Nagoya University. Maybe this is true. I think Morita was professor in Tsukuba University and Jochi University. Yoneda, I don't know, but maybe different university. But at that time, so Gakushuin, Yoneda was a professor in Gakushuin University and the University of Tokyo. At that time, Japan has very strong for that kind of category theory.
There is another important lemma in algebra due to Japanese, Nakayama's lemma.
Nakayama, he is
Nakayama was in Nagoya University.
So in that talk, somehow related to Nakayama's lemma.
No. But Nakayama's factor play an important role in tensor category theory.
Tensor category. So there's some possibility to use the Nakayama's lemma in this talk.
No.
Nothing. Unfortunately, nothing. So
No.
okay.
In your talk, the domain wall is labeled by large M and small m.
Oh yeah,
Yeah.
you are. So
the small m is an object of large M.
yeah. You can understand it as the vacuum state of M. It is a vacuum of M.
Small m is arbitrary or some structure.
You should pick it out. It is a structure. Yeah.
Can you hear me?
Yes.
I have a question. I have a technical question.
Okay.
In your definition of a C module end, so I guess that when C is vac, you recover the old definition of a general end, right?
Yeah.
And if I apply C equals to vac in your, for example, in your diagram, then every lowercase of C is just something trivial. And it seems like your diagram is different from the diagram you displayed to us for the original version.
What do you mean the original version?
Maybe several pages before.
Okay, you mean this, right?
Yeah, this one. There is X and Y, but in your new definition, there is only M.
Okay, I understand your question. Here, you should note that I require this pi to be a diagonal transformation. Okay, and this diagram is just a translation of this requirement. So in fact, I can remove them. Okay, I can remove them because they have been included by this requirement.
Okay.
And here I require it to be a diagonal transformation, and because I need to write down this new diagram, so I did not write down the diagonal transformation requirements.
Okay, I see.
Is there any other questions?
Other question or comment?
Okay, maybe I can I start sharing my screen now?
Thank you very much. So,
Okay, thank you.
Thanks. Now we move to the closing session. So Professor Khan will take some closing speech. So please start.
Yeah, thank you very much. So this is the end of the second joint workshop on quantum science for the collaboration between SUSTEC and Nagoya University. So on behalf of organizing committee, I'd like to thank all the participants, in particular speakers, for their inspiring talks. On the other hand, as one of the participants, I'd like to thank Hayashi-san for his effort for making this workshop in the present form, in particular for inviting outstanding researchers from SUSTEC. Last year, I insisted that it would be also important to invite young people, in particular PhD students, to our activity. I'm very glad to find there are so many talks by young colleagues during the workshop this year. I believe their talks have been at quite high level. The main focus of the workshop is, I think, the quantum information theory, quantum computation, and algebraic, in particular, categorical aspects of mathematical physics. Certainly, there should be many challenges which give us a good chance of communication of people working on such different disciplines. For example, we have heard the name of Kitaev several times during the workshop. I think we should keep organizing this joint workshop since both SUSTEC and Nagoya University has their strengths at quantum sciences. We can expect to enhance our collaboration, not only in the research, but also in the education of PhD students. I hope in your future, we can really meet each other either in Nagoya or Shenzhen. I'm looking forward to seeing you again in the next year. Thank you very much for your attention.
Thank you for good speech. But I want to say one thing. So because in 2019, we already organized a joint workshop between the SUSTEC and Nagoya in Nagoya University.
Yeah.
So in this sense, this is the third time. So
I see. But unfortunately, for 2 years, we cannot see. We can see, yeah. But maybe next year.
I hope next year. So thank you very much. So now I want to close this workshop formally. So, but we can continue somehow free discussion after closing this session. Thank you very much.